I guess so. All right. So we were just reviewing what we were doing last time, which was we defined the radian measure as it's a non-dimensional quantity that will measure the angle, right? And we were saying that the ratio of arc length to the central angle at subtends is proportional, right? So any arc length to its central angle will give you a value of r, right? Which is the ratio of is the radio. It's the radius of the circle in which we find that arc length, right? And the sort of benchmark touchstone for that ratio is the whole circle, the whole circumference divided by the whole way around, which is 360 degrees, or in radians, 2 pi radians, right? And we know that the circumference is 2 pi r, so that ratio is 2 pi r to 2 pi, which is r. That means that, you know, we got our definition for theta. Just solve this equation for theta. And so then we also talked about the area of a sector as being the area of the sector is proportional to the central angle of that sector. So that if you have the whole area of the circle pi r squared to the whole angle, 360 degrees or 2 pi radians, and it's crucial that you measure it in radians, right? When we're doing these computations. Then we can solve this equation, that proportion for the area of the sector, and we get a formula for the area of the sector where this has got to be in radians, right? I can't emphasize that enough, right? And we did some examples, and what were we doing here? Looking at various, our usual touchstone spots going around the circle, right? And converting from degree measure to radian measure. We know that 30 degrees is subtended by an arc of pi over 6 on the unit circle. And so the ratio of arc length to radius is pi over 6 to 1. And that gives you the radian measure of 30-degree angle, which is pi over 6 radians, right? So we'll find 2 positive and 2 negative angles, coterminal with negative 45 degrees. We did that, okay. And find the radius of the circle if an arc of length 20 subtends a central angle of 50 degrees. And we did that. Number 64A. If the area of a sector is 12, then find the radius. And we did a little bit of arithmetic there. And then I sort of sucker punched you here with doing it wrong. And I think most people went headlong. Believe me, I wouldn't do anything wrong, would I? Yes, I would. And I did, so, but then I corrected myself. And then we did this one with the, if you have 3 circles of radii 1, 2, and 3, and you push them together and form and make the triangle formed by their centers, then what happens? Well, you get a triangle whose sides are 3, 4, and 5, right? This side is 1 plus 2, this side is 1 plus 3, that's the side 2 plus 3. And so that's a 3, 4, 5 triangle, which by the converse of the Pythagorean theorem means that's a right triangle, right? If the sides of a triangle satisfy the Pythagorean equation, the sum of the squares of the legs equals the square of the hypotenuse, and what? 3 squared plus 4 squared is 9 plus 16 is 25, that's 5 squared. And so we see that's a right angle, which is crucial for us here, because if we didn't have a right angle, we would have a hard time solving, right? Finding that angle. I mean, it would be determined, and that's what we're about to do when we go to solve triangles. This will be a side, side, side situation. And it turns out we can generalize the Pythagorean theorem to other kinds of triangles. That's called the law of cosines. Okay, so, but since that's a right triangle, we know that the area of the sector is 1/4 of the circle, right? Oh, we didn't even need this r squared theta over 2, although, you know, r is 1, it's, right, circle radius 1. Theta is pi over 2, it's a right 90-degree angle, that's pi over 2 radians. So pi over 2 divided by 2 is pi over 4. But we could also say that's a quarter of a circle whose area is pi r squared with r equals 1, right? And so we get 1/4 of pi is that area. Okay, so that takes us over to the text again. Let me see if I can navigate us over there. Roberto is here. Were you here before? I think you were, didn't I? Roberto. Maybe you weren't. No, yeah, okay, I got you. And great, and Jasmine, yes, counted. Okay, so we wanted to go to Sumatra and look at these problems. Okay, so comparing a triangle. Oops, how do I get to there? I don't know. Here. Comparing a triangle and the sector of a circle. So 2 wood sticks and a metal rod, each of length L, are connected to form a figure below, right? So it's an isosceles triangle. The rod is then bent to form the arc of a circle. With center P, resulting in a smaller angle theta 2 at point P, right? Because you're sort of squeezing the 2 rods together. Find the 2 angles and the difference between the 2 angles. Well, you know, that's an equilateral triangle. So obviously the angle is 60 degrees, right? 1/3 of 180. And what is that in radians? Yeah, pi over 3. Yeah. 180 divided by 3, 60 degrees is pi over 3 radians. Okay, so now if you were to squeeze them together so that the metal rod bows out in the arc of a circle, I guess you could think of it that way, then what would theta 2 be? Well, that's the definition of the radian measure comes to bear, right? So let's start out with that one. And I will switch over to, oh, I've got a legal pad now. Notice that the lines are a little bit farther apart than on my other pad. And how far apart are they? Well, I thought this was sort of an interesting thing. So let's do it over here in the margins, right? So they fall evenly on the centimeter markers between 0 and 7. And how many centimeters are in there? 7, but how many lines is that? 1, 2, 3, 4, 5, 6, 7, 8, right? So each one of these guys is 7/8 of a centimeter. Little applied math there. How's the imagery going here? Yeah, it's a little bit of a reflection there. Should I make this a little darker? Okay. So, oh yeah, what were we doing? We were talking about an equilateral triangle. Okay, so let's say that it's 1 centimeter here. Oh, that was 1 inch actually, wasn't it? Oh, so that's also 1/3 of an inch, huh? 1/3 of an inch. Is that true? 1/7 of a centimeter is approximately 1/3 of an inch, apparently. So somewhere I lost my protractor. I'm now going to find it because oh, there it is. Okay, so I want to make a 60-degree angle. Oh, I guess I want to do it with the center here, right? And I'm using my protractor just because I like a little applied math occasionally. And so would that do it there? I don't know. Yeah. The other way to do this is with a compass, right? So I'm going to take my compass and put the point here and measure out this length, right, like that. And then do it again from this side. And yeah, it kind of matches up with my 60-degree angle there, right? It's not perfect, but it's convincing. Okay, so if these are 1, 1, and 1, it's equilateral, then this angle here is pi/6, right? So now if I were to have the arc length also be 1, let's say I would have to pinch the things together a little bit, right? So I'm going to try to draw something a little bit less than 60 degrees. I'm just going to eyeball it. Use the perfection of your mind's eye. But I want this to be circular, right? And I want this arc to be 1, and these to be radii of a circle of radius 1. That means that this angle here is arc length to radius, which is 1. So, oh, sorry, this was pi/3 over here. Sorry. Did somebody mention that was pi? No, yeah. Go ahead and correct me when I make obvious mistakes. Pi/6 is 30 degrees, right? This is 60 degrees. That's twice pi/6. Okay, so the difference, so let's say this is θ1 and this is θ2. And so θ1 minus θ2 is pi/3 minus 1. That's approximately 3.14159266353, and so on, minus 1, which is 0.14159266353. I think what's the next digit, an 8 or something? Anyway, so that's a pretty small difference, right? But it is a difference. Viva la différence. What else is going on here? Clocks and angles. This is kind of fun. 74. How many radians do the minute hand and the hour hand move between 1 p.m. and 6:45 p.m. on the same day? So this is number 74. I'll just copy that over to our workbench here, huh? So I don't know what that last problem was, but this is 6.1, number 74. How many radians? Do I have that right? Oh. Yeah, okay. Yeah, this was number 72, huh? 6.1. How many radians do the minute and hour hands. Of a clock. Sweep out, this is rephrasing from, what were the times? 1 p.m. and 6:45? And 6:45 p.m., I believe, yes. What does p.m. stand for? Past midnight? No. Gosh, I don't know. Put it in the chat if you know. AM is, gosh, I must know this. Not coming to me. Anyway, so 6:45. So let's draw a picture, shall we? 1 p.m. and 6:45. Okay, so we don't need to make axes. We're not really necessarily in a coordinate system here, but I just sort of want to mark out, here is, noon, 3, 6. Oh, sorry, invisibly writing circles here. Post-meridian. Oh, yeah, so it's having to do with the meridian line. Right, okay. Which we call meridian, AN at the end, but it's just, it must be Latin for meridian, right? Meridian lines are latitude. Well, they actually, the difference in meridian lines are longitude, right? So they're circles that cut through the north and south poles. A plane cut through the north and south poles of the Earth forms a cross-sectional circle, and that's called a meridian. That's, basically the how you know what time it is. Okay, interesting. Okay, in any case, maybe I didn't know that. Huh? You use these things, you never think about them. All right, so what does 1 o'clock look like? Well, the hour hand, sorry, the minute hand is pointing straight up, right? And the hour hand is pointing at 1 o'clock. Let's draw that something like this, right? And so what is this angle? That's pi over 6. Okay, and how about at 6:45? Here, let's mark out 12, 1, 2. These are perfectly evenly spaced. 6. So here's 7. 6:45, you'd be, 3/4 of the way between 6 and 7. And so I'm going to say, here's the hour hand. And here is the minute hand. Is going to be pointing at 9 o'clock, right? I don't know, maybe I should have done this in the same circle, right? Should we do that? So the hour hand is moved over to here, and I don't know, are those perfectly evenly spaced? So I'm going to take the interval between 6 and 7 and divide it into 4 equal pieces. So I can say 6:45 is 6 3/4 of an hour. Okay, so we kind of want to know what is this angle here, and what is Oh, the minute hand is going to make many revolutions, right? So, so what do we say here? The hour hand. So we want to compute the difference in those, right? I suppose we could say that this angle is pi over 3. So I'm going to sort of dissect it into pieces. And then what more do we have to do? Well, another pi over 2, right? And then, I guess 3/4 of a pi over 6. Okay, so sweeps out, it's going to be, I don't know, I'm going to say pi over 3. I'm probably doing this dumbly, but sometimes that's the way I know how to do. Plus, right, so I'm saying that, so you got that right angle there. So pi over 3 plus pi over 2 plus what? 3/4 of pi over 6. Yeah, 3/4 of a pi over 6, right? I don't know. Divide and conquer. So this is eighths. I think 24th is the least common denominator, right? So I'm going to say this is 8 plus 12 plus 3 pi over 24, which is a total of 23 pi over 24. Does that make sense? Yeah, it's 1/4 of pi over 6 shy of 180, right? So 23 pi, that would have been probably an easier way of thinking about it, right? That we're almost going directly opposite would be 7 o'clock, right? And so the directly opposite 1 o'clock is 7 o'clock. So that would be an angle, radian measure pi swept out, right? So how much shy of that are we? Well, 1/4 of pi over 6, which is pi over 24. Take that away from pi and you got 23 pi over 24. How about the minute hand? The minute hand sweeps out many multiples of 2 pi, right? From 1 to 2 and 2 to 3 and 3 to 4, 4 to 5, 5 to 6. Each one of those is going to be a 2 pi. And I think we've got 1, 2, 3, 4, 5 2 pi's. Plus 3/4 of a 2 pi. Right, 3/4 of the way around. That's 45 minutes, right? So that's going to be 10 plus 3/2 or 11 and a half. Which is 23/2. So that's 23 pi over 2. Yeah, that's going to be 11 pi plus half a pi. And I think that's correct. Radians, do we need to say radians? We can abbreviate it rad. The beauty of rad or radian is that it's a dimensionless measure. So you're basically saying, yes, this is a number. I'm thinking of it as the radian measure of an angle. Other problems in there? So they got some applications, wheel revolutions, number 76. Let's just knock that off because we got a little space here. So wheel revolutions. So 6.1, number 76. They ask us, how many revolutions will a car wheel of diameter 30 inches car wheel. That's the word car there, believe it or not. It's a can wheel. I suppose I should fix that. A car wheel. There. Of radius 30 inches. So, 2.5 feet. That's inches. You got to be careful with these little superscript demarcations, because that can also mean seconds in measuring of an angle. But here I mean minutes. Should we just write out the word minutes? Inches. Yeah, see, I even confused myself there. Make as the car travels a distance of 1 mile. So I'm going to just say in 1 mile, all right? That's a question. So I guess we would take, we want to say, how many revolutions? So we want to convert 1 mile to inches. Let's start out with that. So how many feet in a mile? Five tomatoes? Is that how you remember that? I never heard that until about 5-10 years ago, something like that. And some student told me, 5 tomatoes, that's how you remember. What? Yeah, there's 5 tomatoes in a mile. Well, how many eggplants in a mile? That doesn't make sense. But 5 tomatoes makes sense because it's 5280. So we're going to say 5280 feet per mile. Yeah. So this is a conversion factor, right? Because the numerator is equal to the denominator, right? 5,280 feet equals 1 mile. And so we're really multiplying by 1, but numerically we're multiplying by 5,280 because we're converting from a measure of miles to a measure of feet. See why these dimensions are a problem? If only we had some sort of dimensionless quantity for measuring distance. I don't know if there is a dimensionless. It would have to do with the speed of light somehow, maybe. In any case, so now we have feet. Now we need to convert to inches, right? So how many? This is what's called factor labeling, by the way. When you label your factors so you can see what's canceling out. Right, so the feet cancel out, feet divided by feet, those cancel, right? Miles divided by miles, those cancel. So now we've got some number of inches. So then we want to say, how many inches per revolution? Or how many revolutions per inch? Is that a fixed quantity? Yeah, it's a circle, right? So what's the circumference of a circle of 30 inches? Well, 2 pi, radius 30 inches, so 2 pi r is going to be 60 pi, right? So 60 pi inches per 1 revolution. So I'm going to say 1 revolution per 60 pi inches. And notice that, I don't have to wonder about whether to put inches in the numerator or inches in the denominator, because I know I want them to cancel. And then we have revolutions. Do you want a revolution? Of course you do. Okay. With this kind of government, that's a different kind of revolution. All right. So now we need to multiply these out, huh? Do we have a calculator? Oh yeah, I got a little calculator handy. Shall I use the funny one just for the novelty of it? Where is it? I don't know. There it is. Yeah, should we turn it on? Okay, now it's on. Press the clear button. We're going to say 5 tomatoes times 12 inches per tomato. No, that's 12 inches per foot. Times, divided by 60 pi, huh? So I want to go back a notch and say divided by, in parentheses, right? 60 times pi, where's pi? You can't see the whole calculator. Otherwise, you could tell me where it is. And it's kind of badly eroded. There it is. Okay. So I'm getting 336. All right. And change. Okay. So this is approximately 336. And revolutions is what's left, right? The only unit that hasn't canceled out in this product is the number of revolutions, right? So there's our final answer. Does it seem reasonable? 336 revolutions of a wheel with radius 30 inches? That's a pretty big wheel, right? 2.5 feet radius. So yeah, it seems reasonable. What else can we say here? Well, let me just say about this factor labeling technique where, you use conversion factors to convert from what you're given to what you want. That's a very powerful technique. If you use that in the sciences, you can do almost 90% of science. That is, the mathematics of science, if you like. Making sure your units come out right. Yeah, just paying attention to what the units are. Okay, so I think that takes us through 6.1. Let's briefly see if there's anything in 6.2 which we haven't already learned. Oh, there's more applications here. Sorry, I didn't realize it. Oh yeah, look, Pittsburgh, Pennsylvania, anybody? Yeah. Pittsburgh, Pennsylvania, and Miami, Florida lie approximately on the same, there's that word meridian. Yeah, we're so post-meridian, we don't need this. No, it's still morning. We're après meridian, is that? What's the A for? It must be short for before rather than after. A doesn't mean after, A means before. Après, I think, is the French word. Does that have anything to do with the Latin? Oh, I don't know. Shall we go find out? Or I could farm it out as a chat exercise again. I got a couple of Taylor and Mary. We're quick to this. Let's see. So I've got Brave here. If I get rid of this and get rid of that, then I'm here, and I can look up things like this. How about AM meridian? Time and date, AM and PM, what do they mean? Is this where you ended up? Ante, before noon. Oh, I see. So meridian means noon, I guess. It's straight overhead. The circle that's straight overhead, maybe. Ante up. Okay, well, we're 16 minutes shy of the meridian. I learned a new word. How about that? So, okay, now where am I? I guess I don't need to turn that off. I can just, What did I do? What's this other one, huh? Lost it for good, huh? Not sure why that would happen. Oh, I did. I lost my, I think maybe it crashed. Sorry, folks. I don't want Gemini. I don't want my menu. Huh. That's very odd. Oh, okay. So it was here. Sorry. So why does that not appear in my? Where's my mouse? I'm just having a hell of a time here. I lost my mouse now. My computer is misbehaving. Okay. Got my mouse back, and I want I want to see. Okay, there it is. All right. And where were we? We were in Sumatra. Yeah, looking at. Okay. Pittsburgh and Miami lie on approximately the same meridian line, right? That's a line, a circle around the Earth intersecting the North and the South poles, right? Pittsburgh has a latitude, so that's the degree measure from the equator to your position. And that's 40 degrees north, and Miami is only 25.5 degrees north, so it's south of those. And we'd like to find the distance in miles between those locations. And we know that the radius of the Earth is approximately 4,000 miles, or if you want a little more accuracy, 3,960 miles. So, how do we, well, let's see, what's the degree measure difference there, right? So let's draw a circle, and I gotta figure out where my stuff is here, okay. I guess we need a new sheet. Here is a circle. Let's say this is the meridian. I think this is number 77. So let's say that here's the equator, essentially. Should we label that? And this is the meridian line through Pittsburgh, PA, and Miami, FLA. Okay, and they tell us that Pittsburgh is at about 40 degrees. Let's say that's about like so. And Miami is at about 22.5 degrees. So, so here's Pittsburgh. Why not draw them on the right side? I don't know. Here's Miami. So this is, I think they told us 25.5 degrees here. And so then how much further would you have to go to get to 40.5 degrees? I guess 15 degrees, right? So let's label that angle as 15 degrees. So we want to convert that to radian measure, right? So this is number 6.1, number 77. So the distance from Miami to Pittsburgh. And degrees is 15 degrees, right? But we want to convert that to radians by multiplying by pi divided by 180, right? And then we want to multiply that by the radius of the circle. And the radius of this circle is 3,960 miles. Yeah. So theta r is arc length, right? And so this is theta in radians, and this is r in miles. And so that's going to give us radians times miles, which is just miles, right? Because radian is a pure number. And I think that's pi over 16. Is this evenly divisible by 16? So this is going to be 3960 pi over 16. Shall we reduce that? We can reduce by a factor of 4 at least, right? So I'm going to say 4 goes into this 990 times. Yeah, I could have done better, right? So how many times is this is divisible by 2, right? It's 495 times 2. So we can reduce by a factor of 2. And let's go ahead and approximate that, for which I need my calculator. And I need to turn it on and say this is 495 times pi divided by 2. 770.5 miles. So this is approximately 770.5 miles. Does that comport with your general understanding of that drive? I've never been to Florida. I think it's like the only state in the Union. Well, I haven't been to Hawaii or Alaska, but they don't count. I think I've been to every other state. I don't know why Florida is not on my list of places to go, but it's not. Okay, so, or places I've been anyway. I don't expect to go there. So, yeah. Any questions about that? What else we got here? Orbit of the Earth? Well, there's a lot of these kind of questions, right? Find the distance that the Earth travels in one day in its path around the sun. Assume that a year has 365 days. Well, it's actually 365.24. And that the path of the Earth around the sun is a circle of radius 93 million miles. Okay, it's pretty, both of those are almost true statements, right? It's almost a perfect circle. That's more true than saying it's 365 days, I think even. The path of the Earth is actually an ellipse with the sun at one focus, and we'll study that in chapter 11, which we will study. We're going to study the conic sections after chapter 6. So this ellipse, however, has very small eccentricity, so it is nearly circular. Right. One day, huh? So this is number 79. One day, what part of a year is one day? Well, it's 1/365th, right? So how many degrees is that? Well, yeah. What should we start with? One day? We want to convert one day to a distance. So one day, how many degrees per day? Well, there's 360 degrees in a circle, and we're going to divide that into 365 parts, right? So that's kind of why there are 360 degrees in a circle. Why not 365? Did we talk about that before? I think we did. The reason being that 365 doesn't have so many nice divisors, right? 360, a lot of nice divisors. It's divisible by 2 a bunch of times. It's divisible by 3, by 4, by 5, by 6. It's not divisible by 7. I think it is divisible by 8, right? Yeah, 45 times 8. In any case, we could also put the 2, 4 down here if you wanted to, right? So this is days. So 1 degree, this is degrees per circumference. Okay. So the days, this is how many degrees we travel in one day, right? Which is a little bit less than 1 degree, right? The denominator is a little bit more than the numerator, but we want to convert that to radians, right? So rather than even bothering to compute that, let's just go straight to radians, which is pi radians per 180 degrees, right? You see the degrees canceling out now? We got degrees in the numerator, degrees in the denominator. And that's going to give us a degree measure, sorry, a radian measure of how we travel, how far we travel in one day. And then to get the arc length, we multiply by the radius of the circle, which is 90-some million miles, 93 million miles. All right, so there's our computation. Should we do it on the calculator? We shall. Here's the calculator. Turn it on. Should we clear it out? And we've got 365, 0.24. We want the reciprocal of that, right? Is there a reciprocal button here somewhere? A lot of calculators will have a reciprocal button. Does this one have one? No. But we can raise it to the -1 power, right? So if we multiply that by 300, so this is the 1 day is like 0.27% of a year, right? Is what that's saying. So we're going to multiply that by 360 and get the degree measure that we travel in 1 day, which is almost 1 degree, right? Then we're going to multiply that by pi over 180 to convert that to radians. So times pi divided by 180. Oh, that's 190. And then times 93 million miles. Oh, that's a 3. 93. Can we say exponent 6 here? There is an exponent. Here comes a power of 10, right? This calculator is so worn out that I can't read the buttons. There should be somewhere where you get, well, I could just say, 1, 2, 3. Whoops. Now I've done it. 1, 2, 3. So that's, I think I need one more, right? That's 93 million now. Shall we round up here? So in 1 day, we travel 1.6 million miles. So let's get rid of the calculator. Which I'll write in scientific notation because it looks like we're doing science. Does that seem reasonable? Yeah. I mean, are we off by a factor of 10 or so more. I'd know, right? Because this is practically 1, and this is pi times 93. So it's, you know, somewhere between 180 and 360, about halfway. So, all right. That seems reasonable. Geez. So how far did you go today? Yeah, about 1.5 million miles. A long haul. Must be moving fast. Travel that far. Okay, what else we got going here? A lot of fun problems at the end here. I didn't want to skip over them as much as I want to get going. Oh yeah, there's this how Eratosthenes measured the radius of the Earth. We talked about that before. So maybe we will skip on. Oh my gosh, no, there's more. There's important problems. So a radius saw, a blade with a 6-inch radius. Suppose the blade spins at 1,000 rotations per minute, RPM. Find the angular speed of the blade in radians per minute and find the linear speed of the saw teeth in feet per second. All right, we're going to do it. I think this is a must do. Yeah. As we pass from ante-meridium to post-meridium. So this is number 86. The radial saw. I thought I saw a radial. Number 86. A radial saw. A circular saw? I call it a circular saw. I thought I saw a circular saw. I did. I saw a circular saw. Sorry. Write this properly. A radial saw has, they give us the diameter, a 6-inch radius, a 6-inch radius, and spins at, what do they say, 1,000 revolutions per minute? RPM is short for revolutions per minute. Find the angular speed in radians per minute. Find angular speed in radians per minute. Okay, so we have the angular speed is the change in angle per change in time, right? That's a delta for change, just like when we have slope, we write delta y over delta x. That means change in y over change in x. This is change in theta over change in time. So what's the change in theta? Well, per change in time, we want to say 1,000 revolutions per minute, but that revolution is not an angle, right? Or what is it? It's 2 pi radians, right? So we want to multiply by 2 pi radians per revolution. So I'm labeling revolutions ReV, right? And I think, yeah, so that's going to give us radians per minute, right? That's what we want. Notice I don't bother writing radians for 2 pi because it is a pure number. You don't need to write units unless you want to sort of emphasize what you're thinking, right? I think that's just then 2,000 pi. You want to emphasize we're saying radians per minute? Okay, so that's the angular speed. What's the linear speed? Find the linear speed of the teeth on the saw. And so V is simply omega R, right? Because that's, you know, delta theta per delta T times r, and r theta is arc length, right? So that's the distance traveled along the arc. And the radius is half a foot. So do they say what units they want this in? They want it in feet per second, right? So we're going to say 2,000 pi per minute. And they want it per second, feet per second. So we're going to say times 1/2 foot. That's going to give us the distance, the linear speed in feet per minute. Then we want to convert that to seconds. So 1 minute equals 60 seconds, doesn't it? So notice that the minutes are canceling out here. I've got minutes in the numerator and minutes in the denominator. So that cancels out, and that's a 60 seconds. Is that seconds there? So that's going to give us 1,000 pi divided by 60, which is 500 pi divided by 30, or 50 pi divided by 3. Should we leave it at that? 50 pi. Am I off by a factor of 10? It could be, huh? So I reduced by a factor of 2. I got 1,000. I reduced by another, let's reduce by a factor of 10. Half, 1/10 of 1,000 is 100. And then I reduced by a factor of 2. I got half of 100 is 50. And then I still have the 3, right? And these are feet per second, sometimes abbreviated FPS. I suppose you could approximate that, but let's not. I want to get on to other things. Any questions about that before we leave it? Is that good? What are the goodies they have for us here? Speed of a car, the speed at the equator. Yeah, these are all great stuff. How about the speed at the equator? I kind of like that one. So the Earth rotates about its axis once every 23 hours, 56 minutes, and 4 seconds. What you're saying? What about 24 hours? Do we really not have 24 hours per day? I thought that was sort of the definition of a day. Well, this is, in fact, well, one of those is sidereal time. And what's the difference between sidereal time and clock time? You can look that up. That's sort of an interesting topic. So if I go to, I guess I want to just get rid of this and get rid of that. Then we've got our so we're looking up sidereal time, and there's a Wikipedia entry on it. Then there's something from earthsky.org. So yeah, this is kind of a nice description of it. Okay, so the question is, what is sidereal time or star time? Okay, so this when Earth is at position T, position 1, it is noon at the red dot, right? One sidereal day later, Earth has rotated once and moved along its orbit to position 2. For it to be noon again, Earth has to continue rotating for another 4 minutes. All right, so that's position 3. So the Earth has already done one complete rotation before it's noon again, right? So that's what's going on here, right? That sidereal time is different from solar time. So you spin at a lower rate with respect to the stars than you do to our sun. I know our sun is one of the stars, but it's the one that creates day and night. So, and we're very close to it compared to the other ones. So there you go. All right, question answered. Oh dear, we want to go back to then Sumatra and the speed at the equator. So the Earth rotates about its axis once every 23 hours, 56 minutes, and 4 seconds. All right, so it's, yeah, they said 4 minutes off, but it's 4 seconds off of 4 minutes. And the radius of the Earth is the same as before. Find the linear speed of a point at the equator in miles per hour. And that's, you know, sort of relative to what, something. Okay, so this is number 89. Let's go over to pencil and paper, which I think we can get by doing this one. Okay, so the number 89. We want to find the, oh, it's the time is gone, isn't it? Well, let's just finish this up. Oh dear. Okay. So the speed at equator. So the angular speed there is omega, and that's going to be 1 revolution per 23 hours, 56 minutes. So 1 revolution per 23 hours, 56 minutes, and 4 seconds. So we want to convert that. What do they want? They want it in miles. Sorry, they want it in miles per hour. Okay, so we need to convert this. So this is 1. Oh, so we're going to need to multiply that by radians per revolution to get proper. 2 pi radians per revolution, right? So the revolutions will cancel out and we'll have radians. And so we're just going to have to convert this and then multiply by r to get the linear speed, right? So quickly over on the calculator, which is here, we're going to compute 23 plus, what was it, 56 minutes? That's 56 divided by 60, that part of an hour, plus 4 divided by 3,600, huh? Uh-oh. Oh. Oh, it doesn't. So 23.93, okay. And then we want to say the reciprocal of that, right? And then times 2 pi. So let's store that into an answer, into where? A, okay. And so now I'm going to say 2 pi pi divided by, we want to recall what's in A. Oh, why did it do that? Divided by, oh, this doesn't work, huh? Oh. Sorry, 2 pi divided by, recall what's in A. Oh, it just screws up here, doesn't it? The calculator doesn't work very well. Oh, okay, so I guess it is working. All right. So that is our angular speed, angular speed in radians per hour. And we're going to multiply that by the radius of the Earth to find our linear speed. And so that's 3,960 miles. So if you're at the equator, you sort of experience 1,000 miles per hour speed, a little more, which you don't experience if you're, say, at the North Pole or at the South Pole. But you don't feel it, right? Because gravity. Yeah. All right. So I think we're going to wrap it up there. Any questions before we wrap it up? How's everybody doing? Yeah. So this is the linear speed is omega r, and that turns out to be approximately 1,040 miles per hour. Whipping along. You can be pulled over at any time if you live at the equator and issued a speeding ticket. Okay, folks, I guess we're, what are we down to? Oh, everybody's here. Great. I hear the zipping of backpacks and the opening and closing of the door. So I will reappear in my office momentarily if you want to meet me there. All right?
Professor?
Go ahead. Oh, Blake, you're here.
Yeah, I came in late. My Wi-Fi was acting up.
Oh, I'm sorry. Okay, I've got you then. Anybody else come in?
Thank you.
Xavier. Yeah, I think I also missed you. And I think that's it. Yeah. Okay, everybody. Ciao for now. Have a pleasant afternoon, a pleasant post-meridian. Yes.
You too, Professor.
Okay, thanks. Bye.